So this is our AP Chemistry lesson video for Chapter 11. This is Part 1, and I'm going to cover Section 11.1 and 11.2. So we are going to focus on intermolecular forces, and then we'll eventually talk about liquids and solids and how they all relate. So Section 1, we're going to talk about a molecular comparison of gases, liquids, and solids. First, we need to discuss the differences in them because whether or not a substance is a gas, liquid, or solid is based on intermolecular forces. So intramolecular forces within a molecule influence molecular shape, bond energies, and chemical behaviors. So bonds are your intramolecular forces. The physical properties of molecular liquids and solids are due largely to intermolecular forces, the forces that exist between molecules. Okay, so bonds that hold a molecule together. So here's H2O. These bonds, those are called intramolecular forces. But when two water molecules attract each other through hydrogen bonding, that is called an intermolecular force. So bonds are intramolecular forces. Attractions between molecules are intermolecular forces. So the state of a substance largely depends on the balance between the kinetic energies of the particles and the intermolecular forces. So solid particles tend to move the slowest of the states of matter. Liquids tend to move at an intermediate speed, and gases tend to move the fastest. But because solids are closest together, they tend to have the strongest intermolecular forces. Liquids still tend to have pretty strong intermolecular forces because the particles are still very close. Gases do not have very strong intermolecular forces. If you remember in kinetic theory, we assume gas particles have no intermolecular forces because the forces are so small. So the kinetic energies, which depend on the temperature, tend to keep the particles apart, while intermolecular forces tend to draw them closer together. So the faster they're moving, the more they want to spread out. But if they're really attracted to each other, the more they want to stay together with those intermolecular forces. So gases have indefinite shape and volume. They're compressible, they flow, and they rapidly diffuse. Liquids have indefinite shape but definite volume. They're still incompressible, just like a solid. Okay, a lot of you think liquids are compressible, but remember they're still very, very close together. They can flow, they have slow diffusion, and then solids have a definite shape and volume. They are also incompressible, just like a liquid. They do not flow, and they have extremely slow diffusion, and that's due to the fact that those particles are in those fixed locations. So, Section 2, intermolecular forces. The strengths of intermolecular forces of different substances vary over a wide range, but they are generally much weaker than ionic or covalent bonds, which are intramolecular forces. Okay, so it says van der Waals forces, or what we'll talk about, London dispersion forces. They have a relative strength of 1, dipole-dipole is 10, hydrogen bonding is 50, ionic and covalent bonds relative strength tends to be 1,000. Okay, so that's just kind of showing the difference in the strength of an intermolecular force versus an intramolecular force. So the molecules of a liquid must overcome their attractive forces to separate and form a vapor. So for example, when you boil or allow a liquid to evaporate. The stronger the attractive forces, the higher the boiling point. Because you have to think, if they have strong attractive forces, they don't want to leave and become a gas. So we have to heat it even hotter to force them to become a gas. It's similar to when we talk about colligative properties. The melting points of solids also increase as the relative strengths of intermolecular forces increase. So the stronger the forces, the intermolecular forces, the higher the melting and boiling point of a substance. An ion-dipole force exists between an ion and a partial positive charge on the end of a polar molecule. So ion-dipole forces are like when we learned how water dissolves an ionic compound. And we said like the hydrogens of a water molecule will surround a negative ion and the oxygens of a water molecule will surround a positive ion. That is an ion-dipole force because water molecules have a partial negative, partial positive side, but the chlorine and sodium in this case have a full positive and full negative, so they're actual ions. The magnitude of attraction increases as either the charge on the ion increases or the magnitude of the dipole moment increases. And dipole moment magnitude increases as the electronegativities difference increase, which means they're further apart on the periodic table in general if you don't have a chart to look at. So dipole-dipole forces occur when the positive end of one polar molecule is attracted to the negative end of another polar molecule. Now remember, we're talking about polar, we're not talking about full positive and negative, it's a partial positive and negative. So this is just a lowercase delta, and that means partial. So this hydrogen doesn't have a full positive one, it's just partially positive. So see, the negative Cl attracts to that positive hydrogen, but this is just an intermolecular force. This is an intramolecular force. This is a real bond. So we normally will draw intermolecular forces as a dashed line. Dipole-dipole forces increase as polarity increases. So again, the further or the greater the difference in electronegativity of the two elements, then the stronger that dipole-dipole force. For molecules of equal polarity, the forces increase for those with smaller molecular volume. Okay, so the more compact the molecule is. London dispersion forces, which are sometimes just called dispersion forces, are temporary dipole attractions that occur in molecules. Dispersion forces exist in all molecules, whether they are polar or nonpolar. So remember, we discussed this in honors. Every molecule experiences dispersion forces. It's just if it's nonpolar, that's the only type it experiences. But if it experiences dipole-dipole, it also experiences dispersion. If it experiences hydrogen bonding, it also experiences London dispersion. And so it's like an instantaneous dipole that forms in nonpolar molecules, where just for a split second, the electrons might be closer to one atom, so it kind of forms a partial negative. So those are the weakest type. So, polarizability. Polarizability refers to the ease with which the electron distribution in a molecule is distorted. And so by distorted, we mean where we have the more negative side and the more positive side. So see how it's distorted, it's not equally spread out. So molecules with high polarizability have larger dispersion forces. So how do you know when that happens? Well, in general, larger molecules tend to have greater polarizabilities because they have a greater number of electrons and their electrons are farther from the nuclei. So a larger molecule tends to have more dispersion forces. Dispersion forces tend to increase in strength with increasing molecular weight or molar mass. Okay, so you can look at the molar mass. We also talked about how in honors you can look at the length of the chain. That also helps you determine. So dispersion forces, oh, well that's what I was going to say now. So dispersion forces also depend on the shape of the molecule. Dispersion forces increase as the contact between the molecules increases. So for example, this right here is our neopentane, and this right here is N-pentane. So they both have the same formula. It's just this one, notice the molecule is kind of shorter in length. This one, it's a longer chain. So when they line up, this one has a shorter overlap, whereas this one has a longer overlap. So because of this long chain, they can get closer together and they can form more London dispersion forces. So when comparing the strengths of intermolecular attractions in two substances, first consider the following generalizations. For molecules of similar molecular weight or molar mass and shape, dispersion forces are equal unless there's a difference in polarity. For molecules of different molecular weights or molar masses, the substance with more mass has the strongest attractions. So let's look at this one together. It says the dipole moments of CH3Cn is 3.9 debye, and CH3I is 1.62 debye. So remember, we talked about how to calculate dipole moment, although it probably won't be on the AP exam. But sometimes they'll just give you the dipole moment. It says which of these substances has greater dipole-dipole attractions among its molecules? Which of these substances has greater London dispersion? So dipole-dipole is about your dipole moment. Well, notice it gave me the dipole moment. So who has the bigger dipole moment? CH3Cn. That one was super easy. Okay, my greater dipole moment is going to have a greater dipole-dipole attraction. Then it says which of these has the greater London dispersion attractions? So in this case, we need to compare the molar mass of the two. So let's see, did I write it? Oh, I didn't write what it is, but when you add it up, CH3I is going to have a larger molar mass than CH3Cn. So see, the shapes of the molecules should be pretty similar. Okay, this one does have an extra atom, but the shapes overall are going to be pretty similar. Not a single one of them is a really long chain. So in that case, we look at molar mass. So this one is it because it has the greater dipole moment. And this one has more dispersion or London dispersion forces because it has greater mass. And that's just molar mass where you add up off the periodic table. All right, so hopefully those weren't too bad. part C is still for me. So it says the boiling points of CH3CN and CH3I are 354.8 Kelvin and 315.6 Kelvin respectively. Which substance has the greater overall attractive forces? Well, the higher the boiling point, the more intermolecular forces it has. So 354.8 Kelvin is higher, so CH3CN has more intermolecular forces, which makes sense because dipole-dipole attractions tend to be stronger than London dispersion anyway. Alright, so y'all pause it, try this one. I'll assume you've done that and we'll look at it together. So it says, of Br2, HCl, HBr, and N2, which is likely to have the largest intermolecular dispersion forces? Okay, so I can see that all of these are just two atoms. They're all diatomic molecules. Okay, so if I'm looking for just London dispersion forces, I need to focus on molar mass. Okay, so we have Br2, HCl, HBr, and N2. I don't think I wrote the amounts down. I didn't. But Br2 has the largest molar mass. So that's going to have our largest amount of London dispersion forces. Then it says which has the largest dipole-dipole attractive forces. So this is where I need to look for things that are far away on the periodic table. Obviously, this is going to be nonpolar. This is going to be nonpolar. So I have HCl and HBr to choose from. So who are the most different in our electronegativity? HCl. Okay, because remember, the most electronegative element on the periodic table is F. So Cl is closer to F than Br. So that means it's going to have a greater difference from H than Br is going to. All right, so hopefully you got both of those right. All right, so next one is hydrogen bonding. Hydrogen bonding is a special type of intermolecular attraction. So notice it is an attraction. It's not an actual bond. Between the hydrogen atom in a polar bond and a non-bonding electron pair on a nearby small electronegative element or atom, N, O, or F, in another molecule. So y'all, for hydrogen bonding, you have to have hydrogen attracted to either the electron pair on an N, O, or F atom of another molecule. That's how hydrogen bonding works. So here's an example of hydrogen bonding between water molecules. So this oxygen would have two lone pairs, so would this one. And so when the hydrogen attracts to the lone pair on an oxygen, that's referred to as hydrogen bonding. And so hydrogen bonding is really just a very strong dipole-dipole attraction, so it has its own category. All right, so let's look at this one. It says, in which of the following substances is hydrogen bonding likely to play an important role in determining physical properties? So remember, it has to be a hydrogen attracting to the lone pair on either an N, O, or F. Well, methane, it doesn't even have an N, O, or F, so CH4 is definitely not an option for hydrogen bonding. Here, I have N's and H's, so hydrazine is an option for hydrogen bonding. Methyl fluoride, I have CH3F. So y'all, if you look at this one though, the thing is, when you draw it, it's going to look like this. Okay, I'm not going to draw the 3D version of it. And so you may think like, oh, well that H from another one could attract to that F, but the H itself must be attached to an N, O, or F. And in this case, it's attached to a C. So it's not going to form hydrogen bonding. And then H2S doesn't even have an N, O, or F in it. Okay, so you have to be careful. You're not just looking for H and N, O, or F. You're looking for an H bonded to an N, O, or F. So then it can attract a lone pair of another N, O, or F on another molecule. Sorry, that was very wordy. We all know what I mean. All right, so y'all tried this one. I'll assume you paused it, done it, and then we'll look at it together. So we have CH2Cl2. So there's not even NO or F in there, so it can't be the methylene chloride. We have pH3. It doesn't even have NO or F, so it can't be that. We have HOOH. So y'all, when it's written like this, it's trying to show you the order of the bonding. So H is bonded to O, so hydrogen peroxide could form hydrogen bonding. And then we have CH3COCH3. So whenever it's written like this, that means the CH3 is together, is bonded to the C, and the other CH3, and this O is a double bond like this. So notice we do have H's and O's, but the H itself is not bonded to the O, so it can't be acetone. And we'll work on drawing those bigger molecules as we practice. Okay, so in this case, it would be hydrogen peroxide. So hopefully you got that one right. Alright, so hydrogen bonds in water. In most substances, the molecules in the solid are more closely packed than in the liquid. Thus, the solid phase is denser than the liquid phase. However, ice is less dense than water due to the hydrogen bonds it forms in the crystalline structure. So y'all, this is melted wax, and this is solid wax. So notice when you put the solid into its own liquid, it sinks. This is water and ice, so notice the ice floats. So unlike most substances where the solid is most dense, in water, the solid is less dense than the liquid, and that's because of all that hydrogen bonding. It forms a honeycomb shape. So when water freezes, the maximum amount of hydrogen bonds are formed, which makes an open honeycomb shape that lower the density. When the ice melts, the framework collapses. So see, when it forms this open framework, it's a honeycomb shape, there's a lot of empty space. So that's why when you freeze water, it expands, because it's forming all of the hydrogen bonding that it can. Oh, my clicker. Oh, there we go. Did I miss one? Okay. Sometimes my clicker just likes to stop working. Alright, so dispersion forces are found in all substances, and they increase with molar mass and depend on molecular shapes. Remember, the longer the chain, the more London dispersion forces. Dipole-dipole forces add to the effect of dispersion forces and are found in polar molecules. So dipole-dipole, if it has that, it also has London dispersion. And then hydrogen bonding adds to the effect of dispersion forces and tends to be the strongest intermolecular attraction. So remember, hydrogen bonding is just a very strong dipole-dipole attraction. But remember, your London dispersion forces are still present. So none of these intermolecular attractions is as strong as an ordinary ionic and covalent bond. It's important to realize that the effects of all of these attractions are additive. Okay, so remember, your bonds are stronger than an intermolecular force. Y'all like that picture? I like that picture. Alright, so here's just kind of a flow chart on figuring out what your intermolecular forces are. So it says interacting molecules are ions. If there's ions involved, then it says are polar molecules and ions both present. If they are, it's ion dipole. If they're not, it's ionic bonding. So if you just have ions, it's ionic bonding. If you have ions and polar molecules, that's like water surrounding an ion. If ions are not involved, if polar molecules are involved, then you have to ask yourself, is it hydrogen bonding? Could it be HNOF? If yes, it's hydrogen bonding. If polar molecules are involved but you don't have a hydrogen bonding situation, it's dipole-dipole. And then if you only have nonpolar, the only one it can be is London dispersion. But keep in mind they're additive though. Okay, so remember, if a molecule has dipole-dipole, it still also has London dispersion. Right? If it has hydrogen bonding, remember that's a super strong version of dipole-dipole, but still has London dispersion forces. Alright, so let's look at this one. So it says list the substances BaCl2, H2, CO, HF, and Ne in order of increasing boiling point. So if I want increasing boiling point, I want increasing intermolecular forces. So let's go from low to high. Alright, well once I see BaCl2, I can tell this is a metal and a non-metal. So this is made of ionic bonds. So that right there, I already know is probably going to be one of the highest. Okay, because it's ionic bonds. H2, I can see this is nonpolar, so it only has London dispersion forces. So I'm going to put it way down here. I don't know if it's my lowest yet, but we'll find out as we go. CO, I can tell this is polar because it's going to have a difference in electronegativity. It's not nonpolar. So I know this is going to be dipole-dipole. So I'm going to put it somewhere in the middle. HF is going to specifically have hydrogen bonding because it's hydrogen and F. That is stronger than dipole-dipole, but weaker than ionic. So I'm going to put, here, let me put like this instead. So I'm going to put my HF right here. And then Ne, I know this is nonpolar, so it's just London dispersion. So now I have to decide, does it have a lower or higher boiling point than H2? Well, H2 has a molar mass of 2. Ne has a molar mass of 10. So Ne would be greater than H2. And so that's all you have to do. Okay, focus on your intermolecular forces. If you have two of the same intermolecular force, like here, then I can figure out who's greater. In this case, it was Ne has more forces because it has greater molar mass. you try the practice exercise. I'll assume that you paused the video, tried it, and then we will look at it together. So it says, identify the intermolecular attractions present in the following substances. Okay, so we have CH3, CH3. So in this is practically going to be nonpolar because of the C's and the H's are close in electronegativity. You can also draw it and see that any dipoles anyway, because you will have small dipole moments between C and H, but they're all going to cancel. So since this is nonpolar, it only has London dispersion. All right, here I can see that there's an OH. That automatically shows me there's hydrogen bonding. But remember, once it has hydrogen bonding, it has everything. So technically it's still dipole-dipole because hydrogen bonding is a strong version of dipole-dipole, and it still has London dispersion because every molecule has London dispersion. All right, then here again, I can see that hydrogen bonding situation, but it's still going to have dipole-dipole and it's still going to have London dispersion. Now I will tell you, I've noticed on old AP exam questions that a lot of times if they do hydrogen bonding, they won't include dipole-dipole. They'll just do hydrogen bonding, London dispersion, which makes sense because dipole-dipole is hydrogen bonding is just a very strong dipole-dipole attraction. So I found that they will just leave that out and list hydrogen bonding and London dispersion. So don't be afraid to select that as one of your answer choices if this was on the AP exam. So part B says, select the substance that has the highest boiling point. Well, highest boiling point means the most forces. So we can definitely discount this one because it's only London dispersion. So it breaks down to these two. Well, they both have hydrogen bonding, but this one's going to have the higher molar mass because you can see that extra CH2 that it has in there. Okay, so because that one has the highest molar mass, that one's going to overall have the highest boiling point. Because with these longer chains, it can form more London dispersion forces. Even though London dispersion forces are weaker than hydrogen bonding, they still add up to help the overall amount of intermolecular forces. So hopefully you got those right. All right, so that's it for our first video. So hopefully there wasn't really anything new from Honors Chem. This should have just been kind of a repeat of stuff you already know.